this is bad. So just hold on for a minute. All right, so can you hear me now? All right, all right. So this was the last thing I could try. Is still the problem? Wow, what could I do? Okay, okay. So actually, I have shifted internet connections. I rebooted router. I've rebooted my PC, and I don't know what else I could do. Okay, just a second. One more thing, I'll check. All right, so okay, so I hope this time there would not be any problem. And let me mute everybody. Start the recording is anyway started. Okay, so this time it looks like it is working, right? All right, so yeah. Okay, good, 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 good. Right, yep. I'm just keeping my fingers crossed that it doesn't happen again. And okay, so That's about Spark. Like Mahat, we have MLlib. Although Mahat is also being ported onto Spark because Mahat is also performing faster. And also, did you guys check the things which we were doing yesterday? So the results, it took some time, but it did churn on as soon as the course session finished. So in that one, if you go into the home folder under Asgiri, you will see the results where yeah, it was doing a lot of things because those computations are really intensive, and that is why it was taking time. So in this recos folder, you will see that the recommendations are there. Now, these are the recommendations generated by our recommender, which says for the user one, this is the rating, this is the movie which is recommended this much time, this much, and then there is second one, third one, and so on. Okay, and this basically gives us around how many ratings? Around 10 ratings. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, top 10 ratings for each users. Top 10 recommendations for each users. All right. So it did finish after some time because those algorithms take time. They do a lot of computation. Okay. Now, other than that, continuing our Spark. So similar to Mahath, what we did yesterday. Yeah, these algorithms are configurable. There was a command line option where we have mentioned that these are this is what we are trying to do. If you remember what we did here. We say that minus s. This was the algorithm we specified. Similarly, here these were the other algorithms you could try out. Okay, and each algorithm has different kind of configuration parameters, or you can say each algorithm has different kind of knobs to tune. Okay, all right. So similar to Mahat, we have MLlib, and similar to Giraffe, we have GraphX here for graph processing. All right, so to get started with Hadoop, uh, Apache Spark, you can download it from their website, unzip. Here I have downloaded the version which is compatible with Hadoop Yarn with respect to our version, and they have given a specific build for that particular one. Okay, so you can download that one and extract it, and then move that to this location and start. All right, so and then I have already done it for all of the students. You can simply log in and run this in order to get started with Spark. Okay, so all right, let me just close all of this and start the terminal. Okay, and then I'll answer your questions. That's it. Okay, so Abhinav's question is, so Spark is high performance replacement of MapReduce. Yeah, MapReduce means MapReduce component of Hadoop. So does the runtime recommendations work as fast? Like when I watch a movie in Netflix, it quickly pops up a recommended list. Does it keep building up the list at the back end already and store it? Yes. So there we do I mean, whenever you build a recommendation system, you do a lot of things. You do a lot of things, as in the first and foremost which we keep it is product to product mapping. Okay, meaning people who like who like Matrix most likely are going to like other movies. Okay, we keep this list ready, we prepare this list first. This is generally handcrafted in case you have no data, and when you start getting data from the users, you start giving them recommendation based on the other people's behavior. Okay. And the first is we build this kind of a map which is called product to product map. This is our first strategy. Second is you build something like a user recommendation, which we did in this one. In case, and this one is actually pretty straightforward. You generally prepare a map reduce of say there is a user X. So for all new users, this is what we give: product to product recommendation. Okay, all we do is, yeah, I could have actually kept this an exercise that given a big list of users in this one, so we had user ID and we had movie ID. So out of this, if we had to convert this into something like people who like into a movie to movies recommendation, what I will do. Okay, so out of this, what we are given a huge list of movies and user ID. We are given a list of the way we were churning last time. We were given user ID, movie ID, and ratings. Now, out of this, we need to figure out if one person likes movie A, what are the recommendation we can give to him? Okay, so all we need to do is for here for each user 1, we get all the movies. So let's say for user 1 we have movie ID 2, user 1 movie ID, say let's call it M1, M2. This is our user 1, and this is our user 1. So user 1 likes M1, M2, M3. So we prepare, and then there will be a user 2 which says M1. Then there is a user 2 which also likes M4. Okay, now we built a kind of a map reduce in which we put M1 as the key. Okay, and first we group all of them together. Okay, first we group all of them together in the sense that this will become something like user 1 likes M2 and M3. All right, and user 2 likes M1 and M4. So as part of our first map reduce, we'll convert this into this format. Once it is converted, as part of our next map reduce, what we will do is we will say movie 1 comes with movie 2, movie 2 comes with movie 1, movie 3. So we form all the combinations. Okay, we say M1 M2 and M1 M3, similarly M2 M1 and M3, and so on. Okay, now next we will do is M1 and M4 and M4 and M1. Now when we summarize this quickly, we'll do us when we reduce it by this key called movie, what we will get is M1 is followed by M3, Okay, let me do this. Okay, M1 and M2 is our key. M1, M3 is our key. This combination is our key. Okay, this is our key. So so if we form a key like this, which is couple, we pick up two movies out of it and we form this couple. And now we put one here. Okay, and when we sum it up, we'll realize that M2 and M1. Okay, let's just say M1, M3. Okay, yeah, M1, M4, and let's say there was M3 also here. So we'll have M1, M3 as well as M4, M3, and that sort of thing. So when we sum it up, we'll have a frequency analysis saying M1 and M3 come to this will get summed up, and this will become 2 because this and this are same. Okay, so basically what I'm trying to propose here is that we can figure out a movie to movie relationship based on this rating, saying people who like M1 also like M2, meaning how many times M1 and M2 come together. Okay, how many times M1 and M2 come together. If if that is so, this way you can prepare without any Mahat or any other algorithm. A simple summation or average computation would give you a brilliant set of recommendation, provided you have a great set of movies. Okay, provided you have a great set of data, then even a simple computation like summation and average will give you a very decent recommendation. Okay, so this is how a product to product recommendation is done. All right, and so is it clear to everybody other than Susant? Okay, so we basically form which are the two movies coming together, how frequently, and we start giving them as a recommendation. That was without using any Mahat. Also, we do other kind of things. So most customized one is when you know the user. If you know the user, okay, user's history, then you use user's recommendation, and there are many algorithm as we gave. Third case is we have no clue about a user and the history about the movie he's watching. If you have watched Matrix, then I'm giving the product to product mapping, right? The first one. Even if you are just a fresh one, for the first time you are coming to watch the movie, right? If you're coming to watch the movie for the first time, so I can't give even the first one. I can't give the second one, right? Therefore, in those cases, what we do is we basically prepare something called a overall average, okay, for your geography. So we yes, like top 250 movies, top 100 movies, and so on. Okay, and computing top 250 and top 200, you should look at the IMDb's way of doing it. That's actually pretty accurate. Okay, because some of you sent me your answer sheet in which you tried to compute what were the top movies rated, what were the highest rating, and there would be some movies who were just rated by one person, and that person just rated it 5 out of 5, and nobody else has rated that movie. So that kind of anomalies have to be removed when you compute top 250, top 100, top 50, and so on, right? If there is a single product, if you're looking at Flipkart and you go there, you look at the rating, you see, oh wow, this is 5 out of 5, and then you see, oh, it's only rated by one person, so that 5 out of 5 does not convey much. Now imagine this: there is another product, similar product, rated by 5,000 people, and the average rating is 4.8 instead of 5. So, which one you will prefer, the A or the B? A has only single rated 5 out of 5, and the B product has a rating of 4.8 and is rated by around 5,000 people. Yes. So, yes. So, as Swati says, that we will keep something called a minimum number of cutoff votes for each one. Okay, and therefore you will generally prefer a point like B, and so on. So there are multiple algorithms used for computing top 250 and top 100. Yes, or we could have some weight to the number of votes. Yeah, so then it does not remain linear, right? If one person votes, then it's one is just sum it up, other is multiply by number of votes after summation, and then do some sort of a normalization. But still, that problem is quite complex when it comes to a product or anybody, and they keep on doing a kind of ratings. They also, lot of people also bring in the date and time of the rating. What time did the user rate? Most recent ratings get preferential treatment, as compared to the older ratings. They don't get that great treatment because the product might have improved now, or a service might have improved now. Okay, so there are multiple ways of even computing the summation or computing the average. Okay, so I said two things. For even a complex problem like product to product mapping, a simple summation worked. And for as simple as computing top 50, a simple summation may not work. Okay, so you always have to think in terms of the overall output you are delivering. All right, so that's the role of most of the engineers or data scientists or people to figure out what is the exact formula that can do the justice to any of the results. All right, so okay, so we actually digressed, but I don't mind such kind of a digression because these are the things which matter a lot when you will be doing any of these kind of things. Okay, so there was another question. Yeah, yeah, I think I ordered both of them. Good. All right, so before we start, let's start with the basic definition of components. And let me close the door first. Just give me a second. All right, so let's start with the basic concept behind Spark is something called resilient distributed data set. Okay, the way we had HDFS, where a file is located on multiple machines, here Spark has made a big array. It's a which is a representation of the data which is lying on multiple machines. So think of it as a big array in which some elements of the array are on one machine, some element of the array are on another, and so on. So think of resilience distributed data set as a big array. Okay, and in the back end the data might be anywhere. Data might be in the normal file system, data might be in HDFS, data might be in any other form of in any other form. Okay, so the overall idea is to abstract out the complexity of having data located on multiple machines. Okay, for the compute engine, for the computation, you are given a single representation of your data. Imagine the way we had select queries in Hive. Our table, even though it was located at multiple places, our select query did not have to bother about how our table was represented internally, right? So similarly, first concept is resilience distributed dataset, and the acronym is RDD. Okay, so in here you can see these four partitions: one, two, three, four, and in the back end it reads from HDFS, and in the front end user reads and writes to the resilience distributed dataset. Okay, so it could be HDFS, it could be normal file system, it could be actually a variable in the memory, or it could be the data located on a network drive or in a database. So there are many kind of resilience distributed dataset implementations available, but we will focus on HDFS because that is the one which makes most sense. So we have started our Spark. So when you start Spark, it is like this, and it's running on Hadoop 1 right now, and it's running on top of our HDFS. Let's see, is it able to talk to our HDFS? Does it give a sign somewhere? It doesn't say clearly, but I'll show you that it is able to read our data from HDFS and we are able to make it work. So Spark does not only need HDFS, it can run on other systems as well. Okay, so all right, so in this session, if you are setting up on your own machines, if you have set up already a virtual machine locally, you could use this. Okay, and so here you log. These are the instructions to install Hadoop Spark on top of HDFS, or you can yarn, or but you don't have to do the first session because I have already done that and installed it. And all I did was slash user slash lib slash spark slash bin slash PySpark. And this PySpark is essentially a Python client to our Spark. Okay, and I'll be using it quite much here. Just like if you guys are familiar with Python like languages, Python provides you a console where you can immediately type things like a equals to 2 plus 3, and a will be computed immediately. Okay, so Python does it in real time, and it allows you to create functions like def, and you say min, and you say a comma b, and then press tab, return if a greater than b, return a, else return b. Okay, now minimum of, if we now call this function, if we can say minimum of 2 and 3, it's actually maximum I'm trying to compute here. Oh, by mistake I did. So anyway, we can say max equals min, and now I can call max. All right. So I've just reassigned the function, and that is possible using Python or JavaScript. Okay. So these are minor differences in case of Python from C. First, the instead of curly brackets, it's actually the indentation. So indentation here, there is a single tab, which means everything inside min will be single tab. Everything inside if is going to be double tab, and so on. Okay, so it doesn't require a curly bracket. That improves the readability and enforces the discipline. So this is about Python. Okay, and you put a colon after the condition. So I just defined a function min, and I assigned min to max. Now max is essentially same function as min now. All right, so does it make sense to you? So this is a Python console. It's a Python console provided by Spark. It has an additional variable called sc, which is Spark context. Okay, so if you want to read a text file, you remember our word count example. So if you want to read and create if you want to create a resilience distributed dataset, or RDD, representing our big file which we used for word count, then you can do this. All we did was we said lines is this. Now if you just type lines, it tells you that it's an RDD. Okay, it's an RDD. All right. Now, basically, we just created a RDD on top of our existing file. Now, every operation we did on lines, we are operating on an RDD representing our file. Okay. That makes our life easily. Yes, it converted it on the fly. It did not have to convert. It just internally quickly did a memory mapping. Okay, it's sort of like a pig saying a equals to load my file. Okay, here our pig never loaded this file. It just said, okay, whenever in future, if you're going to talk about a, I'm going to assume that you're going to talk about my file.txt, right? So it's the same way what we have just done. Okay, so portions of the lines will be loaded into the memory, and portions of it would be on the disk. Okay, but in this case, by default, since the file is smaller, it has loaded it into the memory. Okay, you can see here it says block broadcast is stored as values in memory, estimated this much. Okay, now, all right, so RDD can be persisted into the memory. Persisting into the memory means having it loaded into the memory and used by other processes. If the file is greater than memory, then only part of the file is loaded. Yeah. So basically, in those cases, I think okay, by default, it tries to load the whole file into the memory. If you do not want it to be loaded into the memory, you have to specify it otherwise. All right. There are flags which say that while loading a file, we have to set that flag that only load first half of the file and so on. Okay, and do not load everything. That's a little bit of a complex part. And yeah, okay. Every RDD, every RDD can recover from node failures. So since an RDD will be represented by multiple nodes, if one node fails, it can quickly recover from that kind of failures. It can have any data type but has a special data set type for key value pair. Supports two kind of operations, transformation and action. The way in case of pig, we said A equals to load something, and afterwards we could say filter A, order A, or we could say things like for each A and so on, right? Similarly, Similarly, here on RDD, we can do multiple kind of operations, and those operations are vaguely categorized as transformation and actions. Okay, now let's just go through the transformation and action. What are the differences between the two? Transformation and action are drastically different operations. So a transformation is something like a mapper, or how should I describe transformation? So if you remember our pig session, probably that will be the closest way of defining Spark. So in pig, the operations, whatever we did, like for example, if you iterate for each or you iterate sort, it did not do anything immediately. It did it did something only when you did store or dump, right? So except for store and dump, all these functions were just done, were not immediately executed. Okay, and whenever we did store or dump, at that time all the pending or dependent tasks were executed. Okay, whatever you defined in past, right? Which are needed for this dump statement. So similar to that, if I have to put the same perspective here, so dump and store are actions while rest of the functions are transformations. A transformation is run on each individual node and does not result immediately. It is run on each individual node and does not give the results back to the Spark driver application. Spark driver application is the application from which the launching of script is happening or launching of command is happening. Right now I have opened a console. That console is the driver application. From that console, I will be commanding the Spark to run my transformation or to run my actions. Okay, again, an action is something like store and dump, which actually makes the execution happen, while transformation is done across the cluster one by one at a time, on the whole cluster, and does not give any results back to the Spark application. Okay, now for example, let's just do something like uh, you know this is not right. Let me try to do. So transformation is something like there are multiple kind of functions which are transformation, such as map. Okay, a map is okay. So lines dot. So here what we are trying to do is what we are trying to do. We are trying to compute. We are trying to compute the length of each of the strings. Okay, and When we loaded the file from HDFS, the RDD is essentially each element of an RDD is the line of that file. Okay, and so you can imagine an RDD, our lines RDD. Lines RDD is essentially array of lines. Okay, it's an array of lines. That's how you can imagine it. And you can define a length function. We can say line length. Okay, and whatever string which pass here, it will do return length string, and that's all. So if we say, so we can quickly test here. So it gives us 7, that is correct. So in the same fashion, now if we have to run lines dot map and we say ll, we are passing the function to the map function, and whatever is the result, we want to store that result in our line lengths. We call it LLS. Okay. Now LLS is one which shows you which is basically computed. It has computed the line lengths here. All right. Now just to say, there is a way to gather all the results. And if you say lls dot collect local lls, okay, and I say, okay, so what I did was I created a function which just counts length of the of each of the line. Then I said that run this function, run my ll function on each of the lines in this RDD. This RDD lines is essentially an array of lines from our big.txt file, and I'm running a function called ll on top of as a mapper. Okay, which means on each element of this array, my function ll is going to be called. Okay, so here the definition of map is different from what you expect. Okay, here, yes, we have Java API as well for Spark, but with Java API, I wouldn't be able to give you demo in real life the way I'm doing it now. Okay, so it's actually I thought that you guys will like it better because it'll give you it will make it work in the real life. Okay, so we defined a function which basically gives out length. Now, in the traditional sense, a map function used to do something like a for each. If you guys have used for each in jQuery or elsewhere, what it does is it takes each element from this array, passes that element to this function. So if you have, okay, let me show you this. I'll just take it out. Alright. If we have this, and let's say lines are Sandeep and Giri, these are the two lines we have, then LLS 0 will become equal to LL, and we call it on Sandeep, and then LL on Giri. Okay, so this is what it does. This is what it does. Okay, is this clear to you? So each element of lines is being applied a function called ll. Whatever is the result will become will become this new array, and hence it will become something of this sort, array of say 7 comma 4. Okay, we got a new array out of an existing array. All right. Yes, so it's basically a Python map function provided by an object called of RDD. This lines is an object of RDD. Okay, it provides you a function called map, which does this. All right. Now, what's the point? You might say, what's the difference between saying something like, so there is approach one in which we are doing this. Okay. Now there is an approach two. Instead of going all the way like that, we could have said iterate a- over our array, which is lines, and then LLS and say okay, LLS dot add this LLE. So what I'm trying to say is there could have been this approach in which we iterate over these lines and do this manually, right? So there is approach one and there is approach two. So do you understand the difference between this? I'll take your question. Yeah, Abhinav, you are right. So it's basically Python map function. Yes, that is right. Sushant's point is one step back. How does Spark decide what the line size is? No, it's basically new line separation, nothing much. Okay. Just like we had those readers in case of HDFS, here there is also an input splitter kind of function which is being used, and you can see that it's actually using one implementation from Java. Okay. Now, question to you is, there are two approaches. One is this, in which we are applying a function called LL on each element of lines, right? This is also doing the same thing. We are iterating over each element of lines and then applying the function ourselves, right? These are the two approaches. And could anybody tell me what difference would it make in case of our problem statement? So here we are saying on top of RDD, we could have said lines, okay, dot collect. Okay, so collect is a reduce function again. Sorry, collect is an action which brings the data from all nodes onto one node. Okay, we call it, let me just call it local lines. So lines is what we created using our Spark context, and we loaded lines into RDD. So lines is an RDD here, resilience dataset, and we are saying, hey RDD, give us all the elements. So now this local lines comes into the memory of a single computer, and we could do things like this, right? So hope you understand the difference between these two approaches. Here, the map is happening on distributed computing. Okay. So we said lines.map and execute this function. So this function is going to get executed on multiple machines independently. The beauty about this concept called map is where we are applying a transformation on each element of an array. Okay, we are applying a transformation in the sense this will get transformed into 7, this will get transformed into 4, right? That's what our LL is doing. The beauty about this is this can be done parallelly by multiple people. We tell we tell the first node that you apply LL on the first set of first records, or if it has say 10,000 records, we could have said on first 250 elements of this array, we delegate the work of applying LL uh, to the first node. We say to the first node, can you apply LL? Can you apply our line length function on these first 250 elements? And then we could say to second node that can you apply LL on 251 to 1000 elements, right? That's what exactly Spark is doing when we are saying lines.map and then we are passing a function. Okay, it's going to take whenever we pass a argument as a function, we are handing over our function definition, and Spark will be taking this function definition and distributing it across the network so that it can be applied parallelly on multiple machines. So that this will make your code travel to each individual node and get it run on each individual node. Okay. Now coming back to what we are doing, so we loaded the file, happy, and now we applied our LL function. Now if we want to bring and check what is there, we can do lls.collect. Collect will get the results to a single node. Okay, now it has started processing things. When we said collect, just like when we said dump or whenever we said store in case of pig, it started process. Similarly, here also it did that. Now you can see local lines. How does it look like? So it brought all the computation we did into a single place. What computation we did? We just did a line lengths on each of the lines on those machines, right? And these are the line lengths of this big text file. Make sense to you? So collect is just opposite of our text file load when we said in the previous screen here text file, where our file got converted into this. Also, there is a function similar to text file. Let's say we have an array 1 comma 2 comma 3. Okay, this is basically our local array representing 1 comma 2 comma 3, right? Now, if we want to convert this into RDD, we say we give our new RDD a name called AR. AR equals to sc dot parallelize, and we say A. So any variable we can quickly convert it into an RDD. Now AR is our RDD. All right. AR dot we could say collect, and it will come back as a local variable. Okay, and this will bring it back. So local v is nothing but 1 2 3. Okay, so while parallelize did is it took our array, distributed, and collect what collected did was it brought the distributed array onto a local machine. Now, on the local variable, your existing program can work happily, but on the distributed one, your program may not be able to work. All right. So, yeah. So, Sushant's question is how does that make faster than MapReduce? Because that's what MR does. So there are two reasons for it. One is the internal implementation in case of Spark. is towards consuming, utilizing your memory as much as it can. While in case of our MapReduce, it is very, very flexible in terms of memory. For example, our Hadoop 1, Hadoop 2, Hadoop 3, or Hadoop 4, all of our nodes are running on a very small memory footprint as of today, something like 64 MB each. Okay, and that kind of memory will, Spark will quickly overflow that kind of memory. One is that. Second reason for Spark to be faster is it has given a lot of control to us. Yes. So it's mostly, one is internal implementation. What's one is internal implementation, and that implementation takes the benefit of memory. And there are other aspects also which have made it faster. So it's basically the internal implementation of Spark which makes it faster than MapReduce. The second is the paradigm. In case of MapReduce paradigm, we had to break down our problem into phases of maps and reduces. There was no other mode of computation as compared to map and reduce. Here, that is broken down. Okay, that is broken down. If you have to combine multiple map reduces, you will have to write something like a UZI framework in which you combine your data from one map to another map, and also the interim data between one map reduce phase to another map reduce phase was always through a file system, not via variable. Okay, that is why the whole dynamics was tuned towards a sloppiness, a slowness, but the whole mechanism was focused towards handling a petabyte of data using multiple machines, where we did not have too much of too much of urgency. Okay, so the whole psychology in building the two tools was different. All right. Now, here we demonstrated a simple case where we took the data from local to RDD and then took it back locally. In MapReduce, uh, speed wasn't priority compared. Okay, yeah. You are right. In MapReduce, the speed, the immediate response time, was not the priority, while in this case of Spark, the speed was the priority from bottom up. Okay, that is correct. So those are difference of priorities which have led to two different products. Okay. So other than map, what map did? Took your function, applied it across the RDD using multiple machine and did the job. So you can see that you can see few things. One, okay. Now look at this function. Let's take this case, okay? In this, if my question to you is, if lines have 30 elements, how many elements will LLS have? Okay. So my question to you is this. right? So yes, so map cannot reduce number of elements, also map cannot increase number of elements. Okay, now in case you do not want certain elements out of LLS, you will use a function like filter, right? And then whenever that function succeeds, okay, whenever that function succeed, then the result will have only those elements. Let's have a look at it. Now we had we loaded AR. AR basically contains our 1 2 3. Now we define a function. We define, we say even only. Okay, and here is our element which says if e percentage 2 equals 0, then return return true, else return false. Okay, now let's just check it locally. Let's just check it. This is true, this is false, this is true. Perfect. So even only is the function which works fine. Now on AR is nothing but an array of 1 2 3. Okay, you can test quickly by saying, because this is small number, so you can quickly say ar.collect. So AR is essentially 1 2 3, and here we can say filter, and we say even only. Okay, and let's say we assign it into AR even. Okay, now AR even, if you want to check what is there inside AR even, you'll have to say AR collect. Why? Because AR even, whatever the newly constructed array, is also an RDD. So you can see A, our AR even is array even is basically has only element number 2, right? So filter's job is to remove certain element or keep only certain elements based on this function definition. So this function is going to get applied on each of the element of an array, and in case if function returns true, that element will be pushed into the new array, new RDD which is being created. All right, then there is something called flat map, right? Flat map is very similar to the map provided by our MR framework, MapReduce framework. This flat map is the one which is similar to our the MapReduce framework. Now what does it do? For each element in input, for each element in input, it can generate 0 or more output items. Okay, it can generate 0 or more output items. All right, so that is the job of flat map. Flat map does it in order to you know so it takes an element from an array and then generates the more elements or no element at all into the output. Okay, so flat map is similar to our traditional MapReduce map, in the sense that the way for a line we split the line into words, and then those words we gave it in the output. Can you please show the output or R even equals filter? Yeah, so R even, what we did was R even equals to AR filter, right? This is what we did. Now let's see the output of, right? So it only contains 2 here. The last line you see, it only contains 2. All right. And similarly, in the input, let's see ar.collect, on which our filter function was applied, is 1 comma 2 comma 3. All right. So filter map is something which converts, which basically gives more number of input. And then group by key is something very similar to our. Is there a way to define a filter or only return true values? Yeah, you can always return a true value. You will have to actually return either true or false. No, nothing other than true or false. Okay. All right. So Sushant's question is, why isn't it contain 3? Why? Because let's have look at our function. Okay. Our function, actually, how can I? So can we have here? Can you have a look at the function? Okay, so filter essentially does is it takes an element, apply your function on that element. If your function is saying true, then it is taking that element on which your function was applied and putting it in the output. If your function says no, okay, your function is the one which is deciding whether an element has to be pushed to the output or not. If your function said no, don't put this guy into output, then the mapper doesn't do that. Oh, sorry, filter doesn't do that. Okay, got it? Got it? Perfect. Now moving on. Similar to that, there is something called group by key, and basically your RDD can either be an array, as we said here, where we said it's a basically big array, or it can also be something like a key value. So an RDD can be either, so an array is what? An array is a mapping between 0, 1, 2, 3 and so on with the values. So we say that give me an element for the index called 0 and it gives you the value. That is an array. Similarly, a big hash table is nothing but similar to an array, in which we say that give me a value for this string. Instead of key being numeric, the key is a big string. That's the difference between a big map, hash map, or an array. Although they are actually very similar in terms of behavior. Alright? So when we say flat map, we give out a big hash table in terms of key and values. Alright? We give out a big hash table in terms of key values, and we'll show you how to do that. Alright? Now, similar to similar to store and dump, there could be multiple functions. Okay, that could be multiple function that could be applied in order to bring the values together. There could be some functions which require all the elements together, and such functions are called actions. Okay, so an action essentially brings the data back to the Spark driver. Okay, actions in run and then bring the data back to the driver from where we are launching all the applications. So there could be multiple kind of actions. The first and foremost is reduce. Reduce takes a function, okay, and applies it at two element at a time. Okay, so any reduce function has to be similar to our combiner we discussed in the MapReduce session. So it will recursively apply your reduce function two elements at a time until there is only one value left. Okay, so reduce function essentially summarizes or you can say aggregates all the values together to give you a singular value. Okay, if we have to create let's say our AR is there, and we say define summation, and in case of summation we have two values, and the summation essentially does is returns a plus b, right? So let's check if our summation is working. So summation is working, so we say ar dot reduce, and our function name is summation. Now you will notice that it returns a local value. It returns our local value. Okay, so local value is 6, 1 plus 2 plus 3. All right, sounds good to you? So a reduce function is something which summarizes your input and brings back data from RDD to a local variable. Similar is count. Count does nothing other than kind of applying count on each individual node and then summing up all the counts from RDD, and hence giving you an accumulative number of elements in the array. So we can say count, and it is going to get applied on all the variables, and it will give you the results. So it immediately gave you 3. You can see the 3. Alright, so the connectivity between this and all the nodes is alive all the time. The launcher box and this. Okay, if you say ar.collect, it is going to bring all the elements to the local machine to display. And if you want to say only first element of R, we want to say ar.take2. So it will give you only the first two elements. Sounds good to you? You can have a look at all other map function transformations as well as actions on the documentation page. Yeah, so this is the Java one. You could have a similar one, similar to our pig, which we have sample here. It gives you the sample of the records. Or you could save it to another file saying this, and if you prefix your file with hdfs as the protocol name, it will save your file into hdfs. Sounds good to you? All right. So is everybody clear about reduce function? Again, let me ask you few quick questions. Which are the valid reduce functions? Or let me ask, is minimum a valid reduce function? Great. Max? So if anybody has doubt about this, just let me know immediately. Okay. Basically, okay, min, max, and say, okay, so average, is average a valid reduce function? Okay, is anybody else changing its opinion? Julie says no. Sushant says no. Who else? Swati says yes. All right. So basically, if you think about average, let's do this. Okay. So let's define our average function. Okay. And we say a plus b into 1.0 just to convert it into float. Okay. So whenever we say 2, 3, oh, I forgot to return. Okay. So just to convert it into double, I have multiplied it by 1.0 and it gives you 2.3, right? Now we have an array of 1, 2, and 3. Now let's say we say reduce and we say average. So 1, 2, and 3, the average should be 2, right? The answer is 1.75. All right? Now you understand. Now you understand that average is not a correct reduce function. Reason being, let's take a case of 1 to 3. So first, it will summarize these two, and this will become 2.5. And then it will compute the average of these two values, and which is 1.75, right? After little bit of try hit and trial, I realized that it does the computation from left to right, not sorry, right to left, not left to right. Okay. Therefore, average is not a good function for reduce, right? Because it gives you the wrong results. You cannot run average function recursively to give the results. All right. So first, before moving on to uh, running a reduce function, make sure that your reduce function is something which is a good candidate for becoming the reduce function. Okay, why? Because when to convert the whole array into a singular value, the reduce function will be applied on the values recursively. Recursively meaning first it will be applied on the values of an array, and then the whole array will because two values will be converted into one, so whole array will be converted into half length, and then again the same function will be applied until we are left with only single value. Okay, so this one, in case of this reduce function, it only takes two values as argument, as opposed to our combiner. Combiner used to take multiple values as argument and give a single value. Okay, let me read out Susant's question. I'm still far from understanding how Spark can produce real-time results. Like for movie recommendation, I need to get bunch of movies IDs, not a single summation operation. Okay, so once you get used to the actions and transformation, you will realize that it is actually pretty simple. All right, once you get used to the transformation and action. So, okay. Now, Abhinav's question is, so all these map, reduce, and filter are Python A? No. Actually, map, reduce, and filter are something provided by Spark, not Python. They are the mapping in terms of Python functions. Okay, but they are not Python library functions. They are Spark's library function. Yes, so Swati, that's correct. So is it clear why average cannot be a correct function? Correct reduce function? Reduce function has to be something which takes two argument, return one, and it has to be cumulative and associative for parallelism, right? Because it has to be applied again and again and again and again until you reach to a singular value. All right. Now let's say we want to count the total number of lengths in this whole file. What are we going to do? So we had lines. Lines is a hue, and we have lines. Let's say start with lines. So lines is nothing but a big text file with all these lines, and we want to compute the total length. So total number of characters in this file, or total number of lengths in this file. So total line lengths in this file. So let's first define something called line length, which takes a string and it is applied. Okay, this is our ll function. So we will apply this function first to convert the each so let's say line length equals line length dot map, and then we say ll. Okay, after that we are going to say define reduce function, sorry, we call it sum lengths. Okay, and we say L1 comma L2, and all it does is it returns L1 plus L2. That's all. And total length is equal to LLS dot reduce sum of lengths, right? Now let's run it. Okay, we get LLS. After that, if you want to just check what is there inside LLS, we say take 10 and it'll give you the first 10 values. Okay, so which is essentially an array of numbers. Okay, now this will basically give you the total length. Now you can see total length is this much. So it has basically these many characters, excluding the slash n. All right. If on the other hand we wanted to say plus 2 because we are summing up two lines, or we want to say in case of this we want to add one more here in because we uh, we are not counting the new line in case of this, so we could basically say this. Okay, okay, now this is the number. All right, so basically we did a very simple thing of counting line lengths. All right, and this is what is going on parallelly. So while computing the reduce, these were the lengths, then two were summed up. It was distributed across the cluster. Imagine that node 1 containing this, node 2 containing this, and node 3 containing this. So this array, if we do it on the single node, this is how it looks like. But if it is on multiple nodes and we are trying to do summation of lengths, this is what it's going to do. Okay. So on one node, the length was computed like this, which is 24, then 14, and then 24, okay, on each individual one. And after that, the driver node picked up 24, 14, and 24 from all these three nodes, and then again applied reduce function on these two, and then on these two. Okay. Although the reduce function does it from right to left, just for example's sake, we have done it from left to right. Ideally, we should say something of this sort. All right. So, okay. So that is how you can apply map and reduces on top of a data and do things a lot of things very quickly. Okay. So I mean here if you had to in case of map reduce, if you remember, if we have to execute map and get the data, it's actually a little tricky. The data finally goes to HDFS, you have to read it again in order to do things. So Spark made it really fast. But there are benefits of MapReduce over Spark. Okay. MapReduce constrains you. MapReduce forces you to do things on the cluster. While people might end up doing a lot of things locally. Here, let's take this example. People might end up doing quickly. So the bad and wrong, you know, effect. You can see that. So what we did was we took lines and we did all of this, right? We could have done all lines. We could have just done, okay. Let's say here after applying Till here, we did exactly what everybody was doing. But after that, silently, what we did was locally, we said LLS and local equals LLS dot collect. And then all we did simply was for E in LLS local, and we said long count equals 0, and for it we iterated over this length and summed up locally. Okay, for each element in this array, we did this. Now this is the common mistake which people do, and every Spark program is prone to this. So the difference between, instead of calling reduce, we did it locally. We brought the data to the local node and we did it locally. Okay. When we say collect, it brought back the whole array locally and then we did it. So this kind of things are quite common in case of a Spark program, and you may not realize it for some time. Yes. So it will run out for most of the cases. It will run out of memory for most of the cases. All right. Why? Because this is happening on a single node, which is local node. Well, this reduce function, when we apply the reduce function to sum the lengths, we did it on multiple nodes. Okay, keep that in mind because that's where lots of people make mistake, and that is probably one of my very familiar interview question. I give people this kind of a code. I give people this kind of a code, you know, I tell them, tell me what is wrong with this. Okay, tell me what is wrong with this approach in Spark. And most of the people can't figure out. They see that, okay, fine, I've used map, that is nice. Then we have iterated over it and we have got the results. All right. So that is something people need to be aware about. All right. So those who are interested, those who want to further go ahead, they should try to implement what I did for matrix multiplication earlier. Here it's far easier. Now, this MLlib, everything, why is it being ported? Because all those scientific library, they use a lot of functions. Say, take a case of simple matrix multiplication. Matrix multiplication requires you to multiply two big matrix into in keeping all of that in memory. If the matrix is really big, it won't fit in a single memory. It has to be distributed across the cluster and multiplied parallelly. So these basic functions like matrix multiplication need to be changed. We cannot straight away use Mathematica or existing library just like that on big data. That is why all those libraries are being ported, and you will see the libraries like MLlib quite often. Okay. On the similar line, generally any R program is not really a good solution for big data because R does it on single machine. Okay. Now let's take a 10 minutes break. Okay, let's take a 10 minutes break and come back. Hi, I'm back. Sorry for a bit delay. All right, so should we start now? All right. So before we move on to other constructs, let's just try to do what we have something called a word count. All right. So instead of loading a big file, let's try to do it simply first. Okay. All right. So let's say we have loaded our file. Right now we are just defining an array for simplicity. Okay. And all right. All right. So this is our word count program as we have done earlier. So for demonstration, instead of saying, we could have said here here sc.text file, and we could have given our hdfs file name, right? Instead of this line, to load the data from hdfs. Here, just for the simplicity's sake, I'm defining an array in memory where it says Sandeep Giri and Sandeep Saha, and I'm trying to do a word count on this file. Basically, it is line 1 and line 2. Alright. Now, first we define a function called split. Okay. And then we apply this function and say ar.flatMap. Why did I do ar.flatMap? Because one element of this array, one element of this array will be resulting on more elements. Okay, it will not be a one-to-one mapping. That is why, right? So let's say, so I say this is my split function. To test it quickly, I call it on sum. So it splits and converts a string into an array of values. Okay, works fine. Now let's use flat map instead of straight map. We use flat map and we say this. Now this will be applied, and let's just to test what it actually did. We collect it, although you don't do it in production. Okay, so all it did was it converted these two elements, Sandeep Giri, this was the one element, this into two, and this into two. So totally there are four elements in this. Okay. Next thing what we did was we converted each of the value here, each of the value into a tuple. Okay. A tuple is multiple values in the bracket. Okay. So what we did was we said, let's define a function called tuple and then call this function using map. Okay. Now if you see what is there in tuple, let's collect it. So you can see that each element has been converted into a tuple. Tuple is multiple values here, and you can see that, right? Okay. Now we apply something called reduce by key. Okay. In each tuple, the first element is taken as a key, and the second element is used for summation. So here we defined a function of summation. Let's test it. we defined a function called summation which sums up two variables. Okay, if you give something of this sort, it says that it should only be given two values, right? Now we, if you see what does our tu contains, tu contains this as of now. Okay, it has a first value and a second value. Okay, so when we are applying reduce by key action, when we are applying reduce by key action on this data, we basically say, so we say output equals reduce by key, reduce tu by key. Okay, and how to reduce? Using our function called sum. Now out is a out is a RDD, which means that out cannot be an action. Reduce by key cannot be an action. That's why here reduce by key should be a reduce by key should be our function. You can see reduce by key. All right. So reduce by key is essentially a transformer. It is not really an action, because had it been an action, our out would have been a value rather than an RDD. Okay, so just to get all the results at a single place, we say out dot collect, and there you go. You can see Sandeep has come twice, Saha has come one, and Giri has come once. You can see the results, right? So that is how you do the word count. Any doubts on this? Do you want me to walk on this file again? Are you comfortable with this? Here the important part is reduce by key takes the first value from a tuple. A tuple is something within the brackets a comma b comma c, and reduce by key takes the first value as the tuple, and the second value is used for summations, passing the arguments here. Otherwise, it will say that it's an invalid input data. Good, good. Moving ahead. So this is how you do a word count using Spark. Okay, you can simply replace this line with this and it will just work fine. You can just re remove this and it will just work fine with our HDFS file. All right, same code will apply. Sounds good. Now moving on to something more important. Well, when I was describing you the MapReduce given in MapReduce paradigm, every time there were more than one questions related to accessing a central storage, right? How would we coordinate between maps? How would we coordinate between reduces and so on? So Spark comes up with a model called broadcast variable. And broadcast variables are the one which makes it possible for Spark applications communicating with each other. So the code running on one node can broadcast to other nodes saying that don't touch this, or saying that I'm doing this. Okay, in the form of variables. Okay, so there is a function provided by SC. The way SC provided us something called parallelize, it also provides a function called broadcast. And we can use this particular, it basically returns a handle for the broadcast variable. And using this handle, you should get or set the value. Okay. You should not be using any other variable if you want to communicate with, because with anything, every other variable inside map function or reduce function or transformation or action, those are local variables. Those are not visible from one node to another. So if you want your, say here, so here somewhere you will say that this is my broadcast. Okay. Here somewhere you will say this is my broadcast variable. Okay. And inside this split we'll say broadcast variable dot get something. Okay. And similarly here we could also use the same function to set it. And this way we will be able to access the common cache of values. So this broadcast variable will be same as on every node and so on. Okay. So for coordination or any cache variable, broadcast is a great idea. And Spark does a lot of clever things. Spark does a lot of clever things in order to make sure that broadcast happens immediately, such as the moment anybody tries to push a new value into broadcast, it immediately invalidates the broadcast variable on all the nodes. And anybody accessing broadcast variable will have to wait till the new value reflects everywhere. So this is a clever implementation of pushing the broadcast variable to all the nodes, making sure that all the nodes receive the value as soon as possible. Okay. So you can say, okay, so we have broadcast variable here, and on that we can say, what is that? We can say, okay, so using the value you communicate with this. Okay. Now if you have to set the value, you have to set using the b dot value, and that's how, and whenever you retrieve the value you also retrieve using b dot value. That's the thumb rule. Okay. Now in the case of, there are cases when each of the Spark application need to immediately give out the output rather than waiting for an action to happen. Okay, rather than waiting for action to happen to accumulate, there are circumstances when we want each of our node to give us the output immediately and to a central location. Okay. And only those kind of outputs can be gathered using accumulators, which basically sums up things. Okay. Where the order of the values does not matter and is always in terms of plus equals to. Okay. Which does not require, so none of the Spark application can read the value back from accumulator. They can only give out. Right? So word count example as I have given you, can use that. And also note that we can use all the libraries of Python as well in case of Spark. All right. So we have used, this is one way. Okay. This is in Python. So there are two ways to do it. One is cleanly defining each function separately or defining anonymous function. This is nothing but anonymous function. Okay. This is anonymous function which is only used once and then thrown away. All right. It's the same thing with the broadcast variable. So what we did was we imported regular expression, loaded lines from HDFS, then we applied a split function on each of the lines and got one word, an array of words. And once that is done, then we removed these special characters, converted the word into lower, and also appended one. And at the end of it, we have the reduce by key. We did a summation here and we got the whole all words. And after the work is over, we saved it use to a text file. All right. So you can run it in a single shot. Probably it would run. So imported it. This is a valid Python program, by the way. All right. The only difference between this and our work is that here we are creating anonymous functions, which is generally a bigger cause of concern. Okay. So you can actually create a separate function that is cleaner than putting a lambda word and then defining anonymous functions. All right. So now you could use a broadcast variable to utilize a coordination between between these all. Okay, so here in this example what we are trying to do is we are removing a, an, and the and all these common frequently used words from the output. So what we have done is we broadcasted as common. Okay, and here we are saying return k0 if not in common value, meaning if it won't be returned. So basically this filter function is utilizing the broadcast variable in order to make sure that these words do not go in the output. Okay, so we splitted the lines by into words, and after that we converted that into a single word, converted into cleaner words, and then we applied a filter function. Filter function checks whether a particular word is any of these or not. If it is any of these, then it does not let it go into the output. And after that is done, it returns the result. We could also utilize accumulator in the sense that if we have to figure out how many times accumulator skipped the results, or something of that sort. So immediately if you say accumulator dot accumulate, it'll give out the results. Okay, the function of accumulator is to give out continuously the output to the central location. It's like having a counter. So for example, Spark application is here. This one had just given out 10, the other one is giving out 20. So continuously these elements can keep on sending the values to be accumulated to the central place. All right. Even before our maps or reduces finish, we will have this variable which is continuously increasing because all others are informing it. It is one way in the sense that Spark application cannot read values from accumulator. All right. So this was a very brief introduction about Spark. Let's discuss something called Spark streaming. So Spark streaming is reading values from various places, and then pushing the data somewhere. Okay, if you remember our discussion day before yesterday, where I was describing that I was continuously reading the data from a queue, right? SQSQ at Amazon, right? So there I was continuously reading the data from Amazon queue. Okay, Swati's question is just wanted to know how do we provide security to these functions that run on various machines? Data seems to be kind of vulnerable to me. Okay, so almost all of these systems, they rely on SSH. Okay, so before we start anything, for example, when we establish the Hadoop cluster, whenever we establish a Hadoop cluster, we establish the trust between all the nodes by the way of defining an SSH key, and we sharing this SSH key. So in the beginning itself, we set up a Hadoop cluster. Now Hadoop cluster itself makes sure that a student can only access the data of a student and nobody else's on every node. Okay. So that way all of these Hadoop makes sure that a user cannot access other users' data. All right. And Spark runs on the same Hadoop, same yarn, which provides the security layer. All right. And hence most of it is fairly okay. One user will not be able to access the data of another user because yarn is anyway abstracting it. Sushant question is the tail function. Yeah. So yesterday I was talking about I did draw something right yesterday. All right, never mind. Never mind. So we were talking about a case study in the case where I was reading data from a message queue on multiple machines. So that was a classic example of stream processing. There's a continuous feed of data coming in via a queue, and you have to read the data using multiple machines and have to do the computation. Okay, so these are message queues on the left, message queues in the form of 0MQ or Kafka, while the other input sources could be Flume, as we demonstrated yesterday, where the data input keeps coming at really fast pace, as and when user is uh, writing into Flume agent, or it could be from HDFS, or it could be from the sources like Twitter. Now, so we might have to read continuously such data and then give the output, do some processing parallelly on multiple node and give the output. To solve this kind of problem, some people wrote discretized stream or called D stream. It basically converts input data into windows of the data, batches of the processed data. Okay, it converts that into batches of processed data. All right. So Spark Streaming receives live input data streams, divides data into batches, and Spark engine generates the final stream of results. Okay. So essentially, what is dstream doing? Dstream is taking the input and converting that into an RDD, a resilience distributed data set, where each element, one element and the another element of this array is separated by the time slot. For first millisecond data, it goes into the first element, second millisecond it goes to the second element, and so on. Okay, although millisecond is not generally the way it is done, it is generally done per second basis. We convert a continuous flow of data. We keep on collecting the data for first second, then next second, and so on, and we keep on adding that into the array. We keep on adding that into our RDD. All right, that way our whole input data is represented as an RDD, and then we can do a lot of processing on top of it, and when we can do this processing repeatedly. All right, let's take a case of this one. So there is a data stream that is coming from left. Okay, it's being stored like this. In RDD, the first element is at time 1, then second element is at time 2, third element at time 3, which is from 0th second to 1 second, then first second to 2 second, then 2 to 3 second, and 3 to 4, and so on. So each RDD in D stream contains data from certain intervals. Okay, so what we did was we took the input which were continuously coming, and we converted that input or accumulated that input into a window of few seconds. All right. Once that is done, so we had original this, and we converted these these 1, 2, 3, 4, 5 records into 3 records. That is uh, creating the windows on top of the existing one. Okay. And this dstream class provides us few more functions such as reduce by key and window. Okay. Just like we had reduced by key, here it also says reduce by key and the window. Okay. To start with, you'll have to create a connection to the input source. Let's say we created a connection to the input source. So this is the class provided by the streaming Spark streaming. And once you are done with that, once you have these lines that is represented as kind of an RDD, we start doing all kinds of operation on top of it. Okay, we can say lines dot flat map, and then we do exactly the thing which we did earlier for counting the words. We splitted it into spaces. Once we got the words, we did the summation and so on. Okay, so basically here, if you see here, this lines is the representation of the input data, and all of these operations you will keep on getting as and when the operations are happening, as and when the uh, uh, as and when new words are coming. Okay, as and when new words are coming, you just have to execute words dot count again and again, and that's all. Okay, so the objective here is to compute the counts of word count every 1 minute. Okay, if you want, if here, so here it's actually every 1 second. Every 1 second we want to count the number of words in the input stream. If you want to do a frequency analysis of the words in the input, so everything else remains same except for this line. Except for these few lines, we do was we create a connection, and then once we create the connection, we have these lines. Okay, and on top of line, we can do all of this. All right. So so in the input, while the data is coming from left to right, the it is stored in this way in RDD. The so first element in RDD is this, second is this, third is this, and so on. And for each one, the flat map operation will give you the word count, and so on. All right. So exactly, so this class, dstream class, is what makes the whole process, the whole continuous operation into windowed operation. All right. So just because Spark makes it possible to do the computation really, really fast, people have started using Spark in streaming, okay, where the computation needed to be done on multiple machines simultaneously, and also where the computation need to be done at really, really fast pace. So in those cases, you could use dstream or Spark streaming. All right. Similar to Spark streaming, there is Apache Storm. Apache Storm is actually faster than Apache Storm is actually faster than your Spark streaming, but for Apache Storm, you will have to set up your own fresh network of only these Apache Storm components. Okay. Though Apache Storm is really, really reliable, but reliable and fast than Spark, but but for Storm you will have to set up everything fresh, and that is generally the inertia. That when I already set up Yarn, why can't I just run my Spark streaming and compute the output? Okay, instead of freshly installing Storm. Make sense to you? Now, there are many companies who are utilizing Apache Storm, like Weather Channel, WebMD, Alibaba, and so on. And Spark is fairly tested across the internet. Alright? There are few more comparisons here. This is more important. So, processing model in Storm is record at a time, while in Spark it's always mini batches. So, no, Storm is not generally the part of Hadoop ecosystem. Okay, it's an independent product, and again, it's also a Apache product. It also has the licensing, Apache licensing. Also to note is the latency in case of streaming Storm is actually pretty low. It's less than a second. Here, in case of Spark, it is still few seconds. Fault tolerance here at least maybe duplicates, but here exactly once. Every record is done exactly once in case of Spark streaming. In case of Storm, it may be every record may be processed more than once. So, and Storm does it for the fault tolerance. All right, and these are historical things. The more important part is when it comes to Storm uh, streaming, Storm is still faster than your Spark. Okay, but since most of the time we are okay with the latency of few seconds, we continue with Spark because it anyway fits into our existing cluster. Is Hadoop getting extinct already with the Spark Storm coming up? Not really. So Storm is a separate product which has been there for quite some time and has been only used for very special purposes. While Spark might replace most of the MapReduce jobs, okay, Spark might replace most of the MapReduce jobs, all right. So in a way, but HDFS and other stuff from Hadoop is still a winner. So examples of Storm, there are multiple. Basically, whenever you have to do a lot of processing, it's better. The downside of Storm is you might have to install a separate cluster dedicated to Storm. Yeah. So yes, Spark is faster than most of the components like Pig and Hive. All the components similar to Pig and Hive Similar to pig in hive, there are components being ported or rewritten. People are writing new components or porting the existing one to Spark. All right. So, what are the downsides of Spark over MapReduce? Biggest downside I foresee is that most of the people who are writing Spark programs will end up overflowing the memory. Second, most of them will actually end up doing stuff on the local node without even realizing that they are running it on a single machine. Okay, that is biggest downside I see. These are the two biggest downsides I see. Okay, so Seema's question is how to decide which one to use. So if you are picking up a new project which is basically the back end and it doesn't require a real time response, you are okay with running it for say 10-15 minutes and you're comfortable in writing MapReduce for it, then go for MR. In case you want a faster response time, maybe a minute or so instead of 15 minutes or 20 minutes, then you go for Spark. So Abhinav's point is we should focus on Spark going forward than MR as its future. Not really, because MR is going to stay for quite some time. There's a huge ecosystem built, and in case MR comes up with a faster processing, they will stay for quite some time. And moreover, in it is still Spark is yet to pick up in case of enterprises. People have not yet moved. Yes, Spark needs a lot more memory as compared to MR. So, no, Spark has moved to the top level project in Apache. It's Apache Spark. And it is actually counted now like a part of the Hadoop ecosystem. And it's done by University UUC Berkeley. Okay, all right, all right. I will take half an hour more because we wasted half an hour today, here and there. So let's take half an hour more and uh, you know discuss few more things. All right. Is that okay with everyone, or does anyone has hard stop? All right. So let's. So I wanted to before I move to NoSQL. Actually, we haven't discussed Uzi. All right. So Uzi is a workflow scheduler to manage Apache Hadoop jobs. So As we discussed while we were doing recommendation at Mahat, we had to do a lot of things such as converting a double colon separated file into comma separated. Before that, we had to download that file afresh and unzip it and keep it and then push it into HDFS, then replace double colons with comma and only select a field and so on. There were multiple things to be done before we actually could run Mahat on top of it, right? Before doing that, before running Mahat, we had to do a lot of things. Okay. And to facilitate all of that, it is not humanly possible to do it every day. Okay. Either we have to write a shell script or we have to use a scheduler like Uzi, which is exactly made for that kind of job. Okay. So Uzi is that workflow scheduler which makes that possible. And workflow jobs are essentially directed acyclic graph, just like our Apache Ant, where we define various kinds of things to do and their dependencies and what to do when and so on. Okay. So workflow jobs are like DAG in case of Uzi. And Uzi comes up with something called a coordinator, which keeps on running in the background and executing things. All right. And Uzi is also integrated with the rest of the Hadoop stack and is scalable, reliable, and extensible. So a directed acyclic graph, as we have already discussed a couple of times, looks like this. 5 depends on 11, 11 depends on 10, and so on. So 5 can only be executed when 11, first 12 will get executed, then 9 will get executed and 10 will get executed. Or you can also see that 2, 9 and 10 can all parallelly be executed, and only after that 11 will get executed, and only after that 5 will get executed. Okay. So but 2, 9 and 10 can be done parallelly. So this way, a directed acyclic graph makes it possible to clearly identify which one to do first and which one to do later. This dependency is what we call directed acyclic graph. A graph with no cycles. A project plan is generally a directed acyclic graph and so on. Okay, let's have a look at how does a Uzi workflow looks like. All right. So Uji workflow is an XML which looks like this. Okay. You start your workflow with a common kind of a XML tag. After that, you say that start to. This tag identifies which action need to be the entry point. And to define an action, you use a tag called action and give it a name. And under that, you have a MapReduce action. There could be multiple other kind of actions. We'll talk about those in some time. In MapReduce, you define who is your job tracker, who is your name node, and other properties which are required to execute a MapReduce. Okay? And we also tell what to do in case word count finishes. we say OK to end, meaning in case this MapReduce was successful, go to end, and end is this. Okay, end is this. Now, or error to, maybe we can say error to something, and it can jump to somewhere else. All right. Also, we can say kill. Something went wrong, and hence we were killed. So this is a single, this is a one action. There could be multiple actions, and we would be jumping to those actions after this word count finishes. All right. So in diagram we can represent it like this. We can represent it like this: start to end and map reduce word count get executed. Okay. So start took it to map reduce action, and once map reduce action happened, then it went to end. Also, here this diagram is actually different from what we are saying. It says in case of error go to kill. Okay, in case of error go to kill. Now, a job could also be a fork. Fork as in run these things in parallel, and all these things, when all these 5 or 10 things finish, then execute something else. So we could also define things for parallelism like this. We say this is my entry point, this is my entry point, and what is this? This is a map reduce task. And once you finish this map reduce task, go to fork. And what does fork do? Fork basically says that these are the two paths of the fork, and then we define those actions. All right. So basically, we first create separate actions, and after we are done with creating separate actions, we stitch them together using things like fork or start to and OK and error to. All right. And here and you can see that in join we say that join is a final job. Okay. And here you can see that when it's okay, then send go to join. When it's okay, go to join. When it's okay, go to join. So second and third, when it finished, they go to join, and join is here. But that does not mean join get executed multiple times. It will be executed only once. Yes, we have a GUI. I'll show you the GUI for creating the Uzi graph. Okay, so the easiest way of executing Uzi job is you log in into any of these nodes and copy this Uzi examples, and then from the examples you can see the job properties, edit the job properties to run, and then you do something of this sort. Okay, in using Uzi job properties we define our jobs definition, and we run. Okay. Now this that is a command line way of doing things. You can also do from the UI. No, Uzi doesn't support JSON. Or maybe I'm not aware, but I have not seen Uzi supporting. So you can go to job designer. Yes. So the work of Mahat which we discussed, that was done manually, one step at a time. You could create the full Uzi job saying download a file, then do this, then do this, and once this is successful, do this, otherwise fail. Alright. So here you can see this is our job scheduler. So Uzi is basically a top layer for all of these. Okay, not only Mahat but all of these. Just like our ant, Apache ant. So we can create our new workflow. Let's call it 24 Jan. Okay, all right. Now here, first, in case of our, what was that? Hadoop job, first thing we will do is we will download a file using shell command. Okay, we say shell and we say in this wget and we say wget whatever was that website, what was that, grouplens.org. Okay, and here we could say add path, as in the file where we want to keep it, where we want to run it from. Okay, and so if we are doing that, we'll say output my file. Okay, so we say done. So this will basically store it locally. Next we will do is, once we are done with it, we will say here, let me just edit this script once more. Here we will also do unzip my file dot zip into, say, my file, right, dot ts, my folder, right. So this I'm giving just an example. Okay, so this is called download and extract. Now next step would be, after you start, you download it and extract it, then you put it into, what do you call, okay, here you say copy to HDFS. Okay, here not delete path but create touch delete, no, not this, create move file, or let me, okay. So you will say, or you can use, actually the fs would be a better idea. Actually that's what it is, create directory, move directory, touch, or the something. Okay, so let's say that you have this, and afterwards, once you are done with this, you might have a pig script over here. Okay, which says convert to comma separated values. Okay, and then you browse and then you say, okay, under restraint, let me just pick up any script for the example case. Okay, I don't have a script. Just for the example sake, let's say this is what we have. So we could prepare, say, download and extract, copy to HDFS, then convert to CSV, and then Once we save it, and here we could also say, although there is no such thing called Mahat, we could say generic, and then we give the command. Okay, or we could actually say here like this, another shell, and we could say whatever Mahat command was there, we could say Mahat. Okay, here goes your command, something of that sort. Okay, so once you create some kind of this kind of workflow, you can run it. Okay, so here this one will get executed, only this finishes, and then and so on. Or you could use MapReduce somewhere. All right, and the fork and other things could also be done parallelly. Say here you could basically say things like this. Just to give an example, I'm trying to do this. So you can see that I dragged the element and dropped on the same thing. Now here the workflow has forked into two. Okay, so this way you can fork it and run it. Once you save it, you can see the workflow as well using the, there is a way to see the workflow. And also once you are done with it, you can schedule the workflow. Okay, schedule the workflow as in you give it a name, you define a frequency, when it is to be done, and then you also define what are the inputs to it and so on. Okay, sounds good to you? That way you can do it from the UI, and this example would be something which basically whatever XML you have prepared, you can upload it here. I'll show you that. Hadoop FS as Giri. All right, so there you can, in the folder I have created somewhere. So under this we have examples, and under examples we have apps. Under apps we have MapReduce. Right, now this is an example of workflow you can have a look at. All right, and you can also see that there is a library containing the code required by workflow and so on. Okay, and under job.properties you can see it has nothing but the location of name node and job tracker, as well as the application path where this will be located. All right. So you can utilize this, and when you say Oozie job, so Oozie has got a server where it gets uploaded and gets start executing. Right? It starts executing after this point of time. All right. So these are the workflow. Anyway, we have seen all of them, and notice that things like Scoop, Hive, everything is there inside the workflow. All right. And that's pretty much about Oozie. You should give it a try to run Oozie and build a confidence in that. All right. Coming back to, so we, all right. Now there is always a big confusion on which NoSQL to use. Okay. So if you only want to do a lot of in-memory computation, you use Redis. Okay. A lot of in-memory computation you want to do, then you use Redis. Everything that is stored in Redis is always in memory. Okay. Sometimes when you are dealing with a very large objects, when you have to traverse a big object, then doing it in memory is the only option. And for such circumstances, Redis is a very good choice. All right. It's not a great choice when your data is too big to fit in the memory. All right. Also, Redis can run on multiple computers simultaneously, and it can utilize the memory of multiple computers. So it is actually similar to Memcached. Memcached drop the performance when the key becomes bigger and the values also become bigger. Redis does not, it does not get hit. Okay. Then there is something called MongoDB. MongoDB is a document oriented database, and it is also a distributed database similar to Zookeeper. It has that whole mechanism of dividing data and running it parallel. Okay. If your data you want to churn or you want to store, if there is something you want to keep in document oriented way, each document, when we say document, is not like Microsoft Word. A document is something, a key value pair, where value can be further key value pairs and so on. Okay. A JSON, for example, is a here in case of a MongoDB, the document is represented in terms of JSON as shown in on the right hand side. It is great when you need dynamic queries. If you prefer to define indexes, okay, instead of MapReduce functions, it gives a good performance on a big DB. Okay. So in those cases, say for example, you have got a website which is running on, say, Drupal, okay, and your website, each page is essentially a big document. It has got header, it has got footer, it has got various kinds of values that need to be displayed. In those cases, you would prefer a thing like MongoDB. All right. And when you have huge data set and you don't require HDFS, you preferably would like to use Cassandra. If you have HDFS, you would like to use HBase. Okay. If you have a huge data set and you want almost SQL kind of access, then you would like to use Cassandra. Okay. And as a something you should note is out of all the databases, including HBase, Cassandra is probably the fastest when the data grows very big. Okay. Similarly, HBase is also, as we have discussed, is similar to Cassandra in the sense that it is able to handle billions of rows and millions of columns. Okay. And when you already have Hadoop, you do not have to install anything other than HBase for your fast read and write. Okay. Okay. Now, regarding the project, regarding the project, so if you go through the project discussion over here, so the objective of this project is to do a sentiment analysis on on Iron Man the movie. Okay. All right. So the project statement is I'm going to give you a stepwise description of how would you do the sentiment analysis of the movie called Iron Man. You may like to do for different keyword. You could use pig instead of hive. I'm you going In this one we are using hive. You could use a different algorithm to compute the sentiment. Here I'm using a very primitive one, and you can start afresh with a different movie and also use your own Flume pipeline to download the data. All right. So Flume pipeline, example of the Flume pipeline is in our home folder, there is a sentiment. Under that, there is a Flume. There are all the configuration file located in that folder to download the data. So you log in into Hue, locate the data. I have uploaded the data, whatever is required for this example here. And once you are done with locating the data, it is there, this data folder. And here under the Hive folder, you will find a, a query called hivedll.sql. And before you start doing anything, create your own database. And after you have created the database, you start executing the statements located in this file. Okay. You start executing the statements one button at a time. A statement means a SQL query. Okay, this one. Also, to execute the statement properly, you will have to download this file locally from HDFS. And this file is located in this folder. You can see that it's located here. Download it locally, and while before running, you will have to say add jar. Okay, this file contains the JSON serializer deserializer, and our data is located in this. Okay, our data is located in this folder, and we are creating an external table from this folder. Okay, Have a look at this SQL, try to understand what it is doing, and then execute one statement at a time. And once you are done till the last point, okay, once you have this table called tweet SBI, tweets BI, you are almost done. After that, you might have to present this data. You could use a driver, Excel driver provided by Hortonworks, or you could use some other mechanism of displaying the data. You could try that out. I think it should be possible. Okay. So here, this is an example which basically shows you how to display the data using Excel sheet. Okay, at the end of the result, you will see that, all right, just a second. So you can, it shows you how is the activity, how Iron Man's popularity is across the globe and so on. Okay, you can utilize this over the map it is showing you. All right, so go through this project and try to do it as soon as possible. The deadline and everything is mentioned on this page here. Okay, so all right, all right. So we are actually one session earlier. We have finished this one session earlier. Generally, I keep a session extra if there are too many questions. Okay, so we generally keep one session extra, and but we are lucky to finish it in 10 sessions itself. So if you have any questions, feel free to connect with me. Okay. Also, please finish your project as quickly as possible, because like with any other software project, you are going to face more hurdles than expected. Today is the last session. All right. Okay. So go through this project. Okay. Everything is step by step, but try to do a little bit of a deviation. Okay. The more the deviation, the better it gets. All right. Yes, yes. Okay. I've gone through your Seema, I've gone through your work, and I'll send it to you. And I've also received from Julie and from others also. I'll send you the feedback related to that. Okay. All right. So we'll send you the feedback for a couple of more, whatever assignments you have submitted. All right. And also we discovered that if you go into user account, under user account, you can see my results section where you can actually see what all you have submitted. Okay. All right. Thank you very much and stay connected. Okay. I'll be sending you the feedback on your work. And in case you get stuck at the project at any moment of time, just drop me an email. And in case you get really stuck and things are not working, we'll set up a hangout session kind of thing, or maybe a go to meeting session itself where I can see your screen. What exactly are you doing? All right. Yes. Yes, Sushant, I had talked about the live project, and that live project, let me have a look at everybody's assignment, and I'll let you know if they qualify for live project. So, Sushant, are you interested in live project? Okay, okay, I'll keep that in mind. Okay, just I'll have to make a note of it because, or just send me an email at Hadoop at KnowBigData if you are interested in live project. Okay. All right. If anybody else is okay, so do write our review here and there wherever. I mean, on our Facebook page specifically, because that makes a lot of difference. And if there has been a mistake from our side or you missed out something, drop me an email and we can fix it. Also, if I mean, stay in touch. As in, we will be sending you a form in case you want to you want to be contacted whenever there is a opening uh, from our knowledge partners. We will forward your resume. Okay. So few things on our side. One is all right. All right. So yeah, one is review your assignments and plan for live project if you are qualifying for it. And third is send submit your CV for if you are looking for change. That okay, form for request. All right. So this I'll do for you. All right. So stay connected and try the forums, and we are fine tuning the forums as well. It was a great batch, and I'm pretty happy with the performance of this batch specifically. Okay. Bye, Sushant. Have a great day. Thank you, Julie. Bye bye. Bye, Sahu. Bye, Nakul. Bye, Swati. Have a great day.